Tonight, it is my pleasure to introduce our speaker. Many of you already know our speaker, Dr. Jeff Dozier. He is a resident of Mammoth Lakes, so many of you see him around town. He's also the Distinguished Professor of Snow Hydrology, Earth System Science, and Remote Sensing at the Bren School of Environmental Science and Management at UC Santa Barbara. And Jeff was actually the founding dean of the Bren School at UCSB, which is now like one of the most highly rated schools in environmental science in the country. And Jeff has been studying snow and hydrology for many, many years. Jeff is a very accomplished mountaineer, climber, and skier, which probably is what got him into studying snow in the first place, I imagine. And if you get to know Jeff, I'm sure he'll tell you lots of great stories about his many adventures. But tonight, we're here to talk about something that many of us have personal experience with. Our winter of snow in 2017. So Jeff is going to give us some perspective on what this winter meant for us in terms of snow, and then the historical perspective on how all that fits in with what he's seen over the years. So thank you, Jeff.
Okay. Yeah, so this, my friend Walter Rosenthal used to point this out, that after a big winter, a lot of people moved out of town. So, and so part of what you're wondering is, when do you think you're going to have to go through this again? And are you still going to be young enough to shovel as much as you did this year? So, the Department of Water Resources has put out a very nice set of graphs. This was the one that they published at the end of March, and this compares the status of the current year with the 1982-83 year, which was the biggest year for which we have decent records. There are stories that back in the 19th century there were some really big years. And also compared to the drought, the big drought year of 2015. And so in the northern Sierra at the top, and the central in the middle, and the southern at the bottom, this year was pretty much on pace with 1983. Except in 1983, it kept snowing. And in fact, the Tuolumne snow pillow peaked on May 5th in 1983. And so if we compare the same graph that was just put out a few days ago, you can see that it's tailed off considerably. And so this was a big year, but it wasn't the record year. So why we care about things like this? One is that in the western U.S., most of our water resources, in fact, come from snowmelt. And this set of bars here indicates the sort of fraction of the runoff estimated in various parts of the country. And the nice thing about snow as a resource is basically the reservoirs in California are not all that large. They're about enough to hold the average annual runoff. So there really isn't a lot of reservoir space in order to last through multiple dry years. And so really our reservoir is the snowpack. And the nice thing about snow, in contrast to rain, of course, is that it hangs around during the winter when the demand for water is low. And then in the spring and the summer, when the demand, mainly the agricultural demand for water, goes up, then the snow produces that water. The other thing, and this picture was taken yesterday while I was working on this talk, and I happened to look out my back window. The snow is also really important in terms of the forest ecosystems. That is, snow is important not just because of what happens downstream of the reservoirs, but the snow also provides a source of soil moisture for vegetation that again lasts into the time when the demand for evapotranspiration is highest. And so our forests would be less healthy if we didn't have the snowpack, and that is if that same amount of water comes as rain, it's going to disappear earlier. Okay, and not only that, the Sierra Nevada is similar to other parts of the world, and so part of what I work on is trying to study the snow in places like Afghanistan and the Tian Shan in northwestern China, but we tend to depend a lot more on remote sensing when we study in those places, and so we tend to use the Sierra as a place where we can test a lot of our methods. And so we sometimes call this the third pole, because like the Arctic and the Antarctic, it is a place where snow and ice dominate the hydrology and the biogeochemistry and the ecology. And it exists, of course, in Europe as part of the third pole, South America, and the largest part of it is, of course, in the Tibetan Plateau. So, first of all, I want to kind of explain where we get, what are the traditional sources of data that I'll use to discuss tonight. So we try to catch rain and snow in a bucket, and we do that. We have snow courses that people go out on a monthly basis and measure at designated places, and Rick Cattleman and Sue Burak and Sue King and I even did surveys with Doug Powell. Some of you remember him. So, and then in addition to the snow courses, there's an automatic way of trying to measure the amount of snow. And that is, you have a pillow that it's essentially a scale that you put at the bottom of the snowpack and try to weigh the overlying snow, and that tells you the amount of water. And then a snowboard, and notice there's a space here between the snow and the board. So it's not what you're thinking of, but it's a place where you can set the board out and then measure what falls on top of it. So what we're typically interested in, especially for water resources, is what we call the snow water equivalent. And that's the amount of water that would result if the snow were to melt. And so that's just the density of the snow times the depth. And if your density is in kilograms per cubic meter and your depth is in meters, you end up with a mass per unit area when you measure the snow water equivalent. But there's a very nice conversion that if you divide by the density of water, that'll give you the depth of the water equivalent. And it's very convenient that there's 1,000 millimeters in a meter, and there's 1,000 kilograms per cubic meter is the density of water. And so a kilogram per square meter is a millimeter deep. So I can do that conversion. I can multiply by 1, even in my head, right? And I like to use that term, that is the water equivalent, instead of the snow water content that some people use. And the reason for that is that Snow is like a soil, and when snow melts, there's liquid water in the snowpack, and that affects its properties. And so we're also interested in the liquid water content as well as the water equivalent, and I usually like to distinguish between those. Okay, and the density of snow, of course, varies. That is, new snow can be as light as 10 kilograms per cubic meter. I've never measured it that light, but I've heard stories of people cross-country skiing in Siberia, and the lakes are the low part of the landscape, and so the cold air drains into the lakes. And so essentially you get a meter of depth hoar on the top of the lake. And if you cross-country ski into it, it's a meter deep and you're skiing on the ice underneath because it's like skiing through smoke. So new snow typically is somewhere in the range up to about 300 kilograms per cubic meter. And then when snow sits in the pack, it densifies. The grains round. They are able to sink together. They compact because of the overlying snow. And so it gets denser and it sticks together. And you know that when you shovel it, right? And then late in the season, we get snow that has been melted and refrozen. And that is even of higher density. And those kind of things happen during a season. And then, of course, if you don't lose all the snow at the end of the melt season, that is when it starts to snow the next winter, if there's still snow on the ground, then, and if that happens year after year, then you will build a glacier. And where we distinguish glacier ice is if the snow compacts enough that it's no longer permeable. It's lighter than pure ice, because there are still bubbles in it, right? Okay. So, things that we measure. Precipitation gauges. It's hard to catch snow in a bucket, especially if it's windy. All right. So generally, I don't believe any numbers that come out of these. Right? Da-Ching Yang, who did some work with me, he works in Canada trying to, correct for the precipitation gauges. And basically what he said is this is what you need, something like this around the rain gauge to protect it from the wind, if you want to believe the numbers. Okay, the snow courses. I like this old picture. It's black and white, and people are on skinny skis with leather boots and super gaiters. And not most of you, some of you have experienced that, right? And so you plunge the tube into the snow and you bring it up and you weigh it and you subtract the weight of the tube, and then that tells you the weight of the snowpack. And the tube is also marked, so you also get a depth. So now you have the water equivalent and the depth, and of course now you have the average density. Right? These are good. These jobs don't have a lot of turnover. Okay. And there's something like 300 of these currently operating. There are some of them that have been abandoned. Back in the 30s and 40s, they established some snow courses down in the San Gabriels, and they just weren't measuring much snow. Pat Armstrong in Bishop, if you know, has written a very nice book on the log of a snow survey. He was a surveyor for many years, and had a lot of adventures in the backcountry. Okay, and then there are the pillows. They used to be made out of butyl rubber, and they were like a waterbed. But they had a big volume of ethylene glycol in them, which is not something you necessarily want in the mountains. And so what they've gone to now is a stainless steel sandwich, which still uses the same principle, but it has a much smaller quantity of antifreeze in it. And this is the one that we have installed up at our instrument site, which is just above McCoy Station at Mammoth Mountain. And there's an animal that we all know that lives around here. It's very curious and very powerful. And so they put a bear net over these snow pillows to keep the curious bears from getting into it. There's a student I know is trying to design a somewhat simpler pillow, and we're testing that up at our instrument site. And then we also have a something to catch the water as it runs out, so we can not only estimate how much melt is going on at the surface, but the rate at which the water is coming out the bottom. All right, and there are a bunch of these. In California, most of these are operated by the Department of Water Resources. In the rest of the western U.S., they're operated by the Department of Agriculture. And then the places that are named are places where we have these intensive snow study sites around the western U.S. Okay, and then if you want a density profile, you have to be good with a shovel, right? And those holes you see in the side of the pit are where we take a 1 liter sample of the snow, and then we weigh that. And so we not only know we get the density at each layer as we go up. And then this here is a snowboard. So if you want to measure the new snow, you put this board out when you think there's going to be a storm, and then you come back the next day and you sample the snow that is on top of the board. And the Mammoth Ski Patrol does this at the Sesame Street study site. So every morning that it snows, they take this kind of a measurement. And the data that Mammoth publishes on their website, the 616 inches, that's the sum of those daily measurements. And I think that measurement's accurate. I just don't know what it means. Because the base depth there is only 130 inches. And so the question is, particularly during the winter, when those two numbers are different, there's a question of, well, where did the snow go? Especially if there's no melt coming out the bottom. And what happens, of course, is it compacts. And you see this. You'll see it snow, and then you look at the pack a day or two later, and it's shallower. And that's not because of any melt has occurred. So that's why we tend to measure the water equivalent rather than the depth. Okay, and this is our instrument site at above McCoy Station, and it's got a couple of these depth pingers on it. So that number in the previous slide for the depth at McCoy, that comes from our site, and I have no idea where the measurement at the summit is made, and I think it might be a guess. And then this is what our instrument site looks like in a lighter winter. This is what it looked like this year. So, okay, so using those kinds of data sources, we need to try to see what's going on. And you know, the first SNARL lecture had art displays for little kids, and then the second one had music, right? And I've got equations. Okay, so the reason for putting you through this is one of the things we want to do when we're comparing measurements of snow at different locations and at different times is that we want to normalize the data in a way that we can make a comparison, a relative comparison. And how many people know what a z-score is? Okay. Oh. So a z-score takes a normal distribution and it transforms it by taking every value and subtracting the mean from that value and then dividing that difference by the standard deviation. And so what it does, it transforms it into a distribution that has a mean of 0 and a standard deviation of 1. And therefore, if you're making measurements of the same variable, but at different locations where the means are different and the standard deviations are different, you might be able to do this to compare them. The problem is with using this is that this applies to a distribution that is normal, that has the normal bell-shaped curve and is symmetric about the mean in both directions. And generally, hydrologic data are not normally distributed. And so we have to deal with that. And the reason they're not, partly, is that some of these variables are constrained to be non-negative. And so you can have a wet year here is, can be 4 or 5 times. That's okay. Sorry. it's not. A wet year, when you have the difference between a warm day and a cool day is usually just a few degrees. They could be 20 degrees or so, but out of, a Kelvin temperature that starts at absolute 0. So it really isn't very much of a change. Whereas, a wet year can have 4 or 5 times as much snow as a dry year. So this is what we call distributions that have a long tail. And this is the distribution at the Mammoth Pass snow course. And you can see the red line would be a normal distribution fit to it. And the problem with it is that there's still a probability left when you get to 0. And so if you apply a normal distribution to these data, you could make a prediction that there would be negative snow, right? And so we got to do something else. So there's the nice thing about distributions is there are a lot of them, but the gamma distribution is the one we tend to use, and that it fits these very large values reasonably well, and it goes to 0 on the left end. The one question this brings to mind is when you say something is some percent of average, what do you mean by average? My suspicion is it's the arithmetic mean, but probably we should use the median, which is the value, half of the values are above that and half are below. So the questions I want to ask about this, that if we look at the state of California, generally there's more precipitation as you go north, but the elevations are lower, and so there's more snow as you go south. And so the kinds of questions that people are asking as we're getting to a warmer climate is, do we have less snow in the spring? And we'll look at that. Is there an increase in elevation in the rain-snow transition? You know, it snowed, it rained here up to 10,000 feet in some of the storms this winter. Is it melting faster? Is there less precipitation? The answer to that is probably no, but it's a question to ask. And then would we expect more interannual variability? So those are the kinds of things we want to look at. And one distinction that Adrian Harpold at University of Reno has made is this distinction between a dry snow drought, which means there's a lack of snow just because there's not much precipitation, and what he calls a warm snow drought, which should be the kind of thing where there's a lack of snow, but either because of earlier melt or because of rain falling instead of snow. Okay. The rest of the talk won't have so many equations, but I thought you should understand what I did. So what I did for each snow course, and each snow pillow for any specific date through all the years is to calculate what the parameters are of the gamma distribution. And what that means, that's the probability density function. So that's the thing that looks like a histogram as a curve, right? And in this case, if it's a normal distribution, then those parameters are the mean and the standard deviation. In the gamma, we just call them A and B. And then if you integrate that probability distribution, that is, if you consider all the values, you end up with what we call a cumulative distribution function. An easier term for that is that's a percentile, all right? So that tells you what the probability is that a value will be less than or equal to some amount of snow, right? And so what I can do then is for every year's snow water equivalent, for any date, I can express that value by looking at its percentile compare to all the other years on that same date. And that way, I can compare different snow courses that have different amounts of snow. So, for example, this is one of the 46 snow courses in the state where we're seeing a statistically significant decline in the amount of April 1 snow over the period of record. And so the way the top graph is the actual amount of snow on April 1st of every year expressed in millimeters of water equivalent, and the bottom graph is the same data, except now I've transformed it into these percentiles. So for example, this year here is about the 50th percentile, so it's about the median year. And then what I'm asking is there a decline in that number over time? But the advantage of doing it by this transformation is that I can do the same thing at different snow courses, and I'm essentially looking at the same set of numbers. And we see that this one is one of those that's declining. And if we look at all of the 46 courses that have a statistically significant decline over their period of record, we see that they tend to be clustered at the lower elevations, And what you mean by a low elevation decreases as you go to higher latitude. Okay, that intuitively that seems to work. And then there are 3 courses that have a statistically significant increase. And one of them is at very high elevation, and then there's one that's a bit of an anomaly. But out of, there are 46 courses that where we see this this decline in over the years that we can believe, and there are only 3 where we see an increase. And so you can kind of draw that in a perspective with elevation on one axis, the latitude on the other axis, and then the slope of the decline. And and that number of, say 6 times 10 to the minus 3 per year, that would mean in a decade you would change the snow by 6% in the percentile. So it's not a small number. Okay, what about the problem of earlier melt? Well, now we can use the snow pillows. So this is a graph on the left with what the snow pillow reads at Tuolumne Meadows, and it's for 3 different years. It's for '83 and the current year, and then 2004, which is kind of a normal year. And what you see are that the amount of snow on the ground kind of steadily increases as you go through the years. And then it melts, and it melts pretty rapidly. And the other thing that you notice is that when it melts later, it melts faster. In other words, the decline in the 1983 was pretty rapid. And the reason for that is that you're pushing that melt out to the part of the year when the days are long, the sun is high in the sky, the temperatures are warm, and so it melts faster. Whereas when it melts earlier, it tends to melt more slowly. All right? And then what I've done on the right-hand graph is I've taken the data from the snow pillow, and I've looked at the daily differences. And where the daily differences are positive, I'm saying, aha, I've had a storm fall. And where the daily differences are negative, that means some of the snow has gone away. And mostly we think it goes away by melt. There is some sublimation, that is some direct transfer of ice into vapor, although that usually is about no more than about 20% of the total. And then it can also be scoured, but they usually try to put these snow pillows in a place that are a little bit protected from the wind. And what we see here is, and then I've just graphed the storms in black with the bars going up and the melt in red going down. And what we see that's a little bit interesting this year is we haven't really had any significant midwinter melt, but we did start to melt earlier. That is, this large red blob of melt is occurring earlier than it did in '83. Okay, so what I've done in this case is compare this year with '83 by looking at these percentiles and then drawing a histogram of those percentiles for all of the pillows where I had data. And so what I chose is that +1 places where I had at least 30 years of data and where I had measurements on April 1st and on May 1st in both the current year and in 1983. And what we see in 83, this blue line, there were a large number of snow pillows that were right at the top of their historical record. That is, that had percentile values out in the 95th percentile or snow. In this year, there were some, but there was a smaller number, and there were more courses that had a lower percentile, although almost all of them were above the median. So it was a big snow year. It was a big snow year pretty much everywhere, but it wasn't as concentrated as it was in 1983. Okay, so what does the Department of Water Resources do with these data? Well, what they do is they use a statistical method to predict runoff. And one of the questions is, well, how well do they do? And so what this is a graph of the forecast error. It's the denominator's cut off at the bottom, but what I'm doing is taking the forecast. From it, I subtract what we call the full natural flow. And that's a calculation of how much water would flow past the reservoir if the reservoir weren't there. And also accounting for any upstream diversions. And then divide that by the full natural flow, and then you get a percentage error. And what we see, and then I look at the probability plot of those errors. And at 0.5 on the probability plot, that's the median error, right? That is 50% of the values are above, 50% of the values are below. And the forecast error is pretty good. All right. Okay, it's a statistically based method, so you would hope that it would do well most of the time. The problem is that this also has a long-tailed distribution. So, for example, if we go up to the 0.9 on the probability scale, now we're at 0.5 on the error. So what that is saying is 1 year in 10, you're going to make an error that is 50% or greater. Okay. On the low end, we're saved a little bit because the biggest error you can make in the negative is 100%, right? Whereas on the upper end, you can make an error. So sometimes we make a mistake. So, when you tell your children, you're going to go through life and you're going to make mistakes, but try not to make the big ones, okay? All right? Some people have asserted that some of the forecast error is due to a forecast made on April 1st and then storms in April happen. And that may account for, but that's going to be a negative error. The forecast is going to be too low, and so that's down here. The ones up on the right-hand side, this is where they're just overestimating the amount of snow in some years. So what this brings us to is, are there ways that we can do better? And there are a couple of things that we can measure by remote sensing. One is, from satellite, we can measure snow-covered area. We can tell whether the snow is there or not. And then there's been some nice stories in the Mammoth Times and the Sheet and the New York Times about the Airborne Snow Observatory that Tom Painter is the PI of. And basically what they're doing is they're measuring they're measuring the snow depth from a Lidar, and then they're multiplying by density to get the snow water equivalent. And the reason for doing that is that the snow pillows and the courses may not represent the distribution in the topography. So a couple of things. One is they're all on flat ground. And you really have to, because the snow pillow's got a tower that it uses to transmit data and stuff, and you put that in a slope and the snow creep will just tip it over. And also you got to have places where you can get to where there's no avalanche danger. And they don't cover the highest elevations. And so in 2011, we can see in July that there's still snow in the Tuolumne and the Merced, but the snow pillows have melted out. And so especially by the 18th of July, and we can see that in the snow pillow record in all of the pillows that by then on July 11th, there was one pillow that still had snow in it, and on July 18th, there were none. And yet, there was a fair amount of water that came down from then. And so a friend of mine is now retired, but he was the manager of the Hetch Hetchy Reservoir. And Bruce McGurk, he kind of recognized the problem. All of his pillows had gone to zero, but you can hike around and you can see that there's still snow in the mountains. And so the question is, can you release some of that water in order to generate hydropower, or do you have to hang on to it so that when you go to San Francisco in November, you can take a shower? So, like I said, from satellite, we can measure snow-covered area, and this year there was a lot of it. And then the Airborne Lidar, so what it measures is it's a Lidar altimeter. So it shoots a laser beam down, it shoots a pulse, it measures the time it takes for the pulse to come back to the aircraft. And so what that allows you to do is measure the elevation of the surface underneath. And if you fly when it's dry, you get the bare earth elevation. And then when you fly when there's snow on the ground, then you get a higher elevation, and you subtract the two, and you get the depth. And you also, when you're shooting through trees, you get some return from the trees themselves, but that actually helps you understand something about the characteristics of the vegetation. And in doing this, so the left-hand column is April, May, the rows are April, I'm sorry, the left column is April, the middle column is May, and the right column is June. And then the rows are 2014, 2015, and 2016. The data have not yet been released for 2017. And you can see in the middle row in 2015 that there wasn't much snow. And this is a map of the snow water equivalent. So it's using the Lidar and then multiplying by the density that they get from the courses. This turned out to be important. So they started this investigation in 2013, which is up in the upper left, and the blue bars are the measurement from the Airborne Snow Observatory, and the black line is the data from a set of about 10 snow courses spread around the basin. And so in 2013, everybody was pretty happy because they said, well, you know, we did this really complicated experiment and it told us what we already knew, right? And then what happened in 2014 and in 2016 again is that the Lidar showed a lot more snow in the basin than the snow pillows did. And particularly this was snow at the higher elevation. And so what happened as a result of this is that they actually changed their forecast and they released some water that they didn't know they had until they had the Lidar flights. And the hydropower generation they make about $125,000 a day when they're able to do that. So there's a big advantage to doing a little better sometimes. Okay, there's another way that we've done with satellite that we can reconstruct the snow after it's gone. Another lecture, another day. But it does show that it gives you a different answer than you would get from just interpolating from the snow pillows. And then there's a model that NOAA uses that in areas where there are not a lot of good measurements doesn't do very well. But this reconstruction works pretty well in terms of comparing it with streamflow. So if you note that in every basin over the years, the black bars are at least as high or higher than the blue bars, which is the model, which is sometimes pretty low, and then the measurement based on interpolation. The only problem is this doesn't give you a forecast because it's back calculated. Okay. So this is my last slide, but this is something I just thought of this afternoon, and so I put it in. So one of the problems that we face is in the future, will the pattern of the snow be different? And in statistics, we often make this assumption of what we call stationarity. And that is that it means that if you establish a statistical relationship for what went on in the past, that you can believe that relationship as you go into the future. And that's the assumption of stationarity. And the problem is that if there's something that is changing, so in other words, if we're using a statistical relationship between a bunch of snow, a dozen snow pillows and snow courses spread around the basin to predict the runoff, and that pattern of accumulation is changing, then we're going to be in trouble. And by being in trouble, what I mean is if we don't do something that's different to get a better handle on the amount of snow, our performance is going to get worse. It's not just going to stay the same. So I was asking myself, do we see any of this in the data? And so what I took was the Mount Rose snow course, which is where the whole tube was invented by James Church, who was a professor at the University of Nevada, Reno. And that course was established in 1910. So it's got 107 years of data. And so what I did was to calculate this statistical distribution over a roving 30-year window. So I took the 30-year window from 1910 to 1940, and the middle of that would be in 1925, and so that's when my analysis starts. And I calculated the two parameters of the gamma distribution. And the A parameter is basically a scale, and the B parameter is basically a spread that looks at the variability. And so the question is, are those numbers changing over time? I don't know. What do you think? Because if they are, that means that we really do need to try to, based on first principles, is actually figure out how much snow is in the watershed. Right? Okay, thank you. Nobody's asleep. Oh, very good. Yeah.
I was a little startled at the relatively low significance of sublimation.
Well, so we've measured it up at our site here. And that's why we have the lysimeter in the bottom, that we can tell from the pillow how much snow is disappearing. And then at the bottom, we can tell how much of it is coming out as water. And the difference is sublimation. And 20% is not a small number. Probably in the White Mountains, it's greater. Probably in the forested environment where there isn't any wind, it's low. But yeah, it is something that we try to take care of. Yeah. Oh. How does snow melt? The sun shines on it, and it heats it up. And so where does the white go? Yeah.
I want to be clear on what Lidar does and doesn't do. I understood you to say that Lidar is measuring the depth of the snowpack, in other words, by subtraction from
Yes.
the distance to the normal terrain.
Correct.
In order to get accurate figures, you have to combine that with snow water equivalents from actual physical.
You do need to multiply it by density, and so they get those from the snow surveys. They get density. Many of the pillows have depth pingers on them, so they get density from those. They're only getting a few density measurements.
There's no way Lidar itself can actually, by looking at a broader spectrum.
No, it doesn't penetrate enough. Now we are working on it with radar, but we've been working on it for 3 decades. The thing that helps, though, is that most of the variability is in the depth. And so in all this kind of stuff, you always have to remember that better is the enemy of good enough. and so yeah, there's some uncertainty because of the densities, but especially in the spring, density tends to be more conservative, and we're working on it. It's a hard problem, especially when the snow gets wet. Yeah.
Were you able to raise your boom up at the McCoy station high enough to be above the snow level, or was it very?
No, in 2006, our down-looking radiometers were buried, And so what we did after that is we moved the boom up on the railing of the platform. It was on the floor of the platform. And we were measuring albedo by measuring the amount of radiation that's being reflected. And one day I looked at our web log, and our albedo had gone to 0 because the down-looking radiometers were buried. Oh, in the back.
You measure albedo, you do it in visible light or
We do the whole spectrum. We do it separately in the visible and the near infrared. And there's a whole nother lecture I can give on what's an albedo and why do you care. But pardon?
you get different information from different?
Yes, and the reason is that in the visible part of the spectrum, ice is really transparent. And so the grain size doesn't affect the albedo very much, but the contamination by dust and soot changes it. When you get in the near infrared, ice itself is more absorptive, so the dust doesn't matter so much. But now the grain size makes a difference. So we want to be able to separate those two effects. Okay, yeah.
As a hydrologist, do you get involved in the proportion of snowmelt that is absorbed on site back into the ground, and what proportion ends up as runoff?
I think about it a lot. It's a tough thing to measure. The hardest part of the whole hydrologic cycle to measure is what's going on in the groundwater. So one of the related questions that people ask me is a drought over? And in terms, the runoff will fill the reservoirs, but there's been a lot of groundwater withdrawal in the Central Valley over the 3 drought years. And there's, subsidence of 70 centimeters going right through the area where the high-speed rail is supposed to go. And so Steve Margulis at UCLA has done, and he and his students have done a very interesting analysis in which they looked at the difference between the amount of snow and the estimated evapotranspiration, and assumed that difference, because the evapotranspiration was greater, was made up with groundwater withdrawal. And his estimate was it'd be 4 or 5 good years to recharge. Yeah.
Can you give us a brief overview of the subsidence?
Now I get to go to the Eastside Bakery.